my name is Kirill, and I'm here to present the work on Urwasm project. Dan, thank you for the introductory talk. First, a short introduction for people that don't know what WebAssembly is. WebAssembly is a low-level language, which is a compilation target, and it was designed for browsers. It has binary and text code formats, and it was designed with kind of in a hardware-independent way, and has a very simple specification. It is supported as a compilation target by C, Rust, Go, and a number of other languages. And for some other languages, their runtimes that are written in C were compiled to WebAssembly. So for example, you can run Python directly in your browser. There is a project called Pyodide that lets you do that. And all of these properties make Urwasm, well, they make WebAssembly an attractive language to host on Urbit. And Urwasm project is about running WebAssembly in lock reasonably fast. It doesn't have to be blazingly fast, but if you can do it reasonably fast, it's going to be good enough. And this is what I presented back in January. It was a WebAssembly interpreter in Hun, and it kind of dealt with the first part of the problem, where you can run WebAssembly in lock. However, it was unreasonably slow. The way it was implemented, it was with a function invoke, which as arguments took the name of a function that you want to invoke from a WebAssembly module, a list of WebAssembly of Wasm values, which are 32-bit or 64-bit integers or floats, and a stored noun. And stored noun is just a noun representation of Wasm virtual machine state. And when you invoke a function, if the invocation was successful, you get a list of results and a new store noun. So basically, the invocation of WebAssembly function is stateful. You get a result, and you get an update of the Wasm VM state. It supports the entire Wasm specification as of January. So you have FFI, you have SIMD instructions, but it's really slow, and you have to jet it. But before I describe how I jet WebAssembly, I wanted to go quickly through how WebAssembly is actually evaluated, both in browsers and how it used to be evaluated in Hun. So typically, when you compile higher-level code to WebAssembly, you actually get two code files. You get the WebAssembly module, which has the bulk of all the code, and it's low-level. The functions, they can only return fixed-size integers or floats. And so there is no notion of a string or a byte array in WebAssembly as is. But also, another file that is produced is JavaScript code. And that JavaScript actually provides a higher level wrapper for the WebAssembly. And then you just put this project in your, you put those two files in your web project, and you just call higher level functions from JavaScript. And under the hood, JavaScript calls functions from WebAssembly. And you could do the same thing in Hun. Well, first, let's actually go through an example from Rust. Let's say you have a function foo from string to string, and it's compiled to two functions, actually. One is in WebAssembly. It's a foo function that takes two 32-bit integers and returns nothing. And it also exports a bunch of other functions called malloc, at the pointer, free. And you cannot really use this directly in your browser. However, the compiler also provides a function foo in JavaScript, which takes a JavaScript string and returns a JavaScript string. And then this function actually performs a bunch of WebAssembly invocations. So it calls malloc in order to allocate memory on the heap. It calls add to stack pointer to allocate memory on the stack. And then writes the string that you provided into the memory. And then it calls foo, the WebAssembly version of foo, which it does not return anything. However, it updates the state of the virtual machine, and then you can read out the output string from the memory, and then you free it. And this was also done in Hun, rather straightforwardly. So when you instantiate a WebAssembly module, you get a store noun, and then on each invocation, you provide input parameters, and you get output variables, and your store noun is updated. And then you can just chain those invocations one after another. And so, like in previous example, if you wanted to implement a higher level foo function from string to string, you basically needed to chain 5 WebAssembly invocations. And it worked. It just was really slow. And the question is, how do you jet the invoke function effectively? Well, kind of the knee-jerk reaction, I guess, is to try the invoke function itself. However, it doesn't really work because notice that the invoke function, it takes the store noun and it produces a new version of the store noun. And at least right now, the jetted words are read-only, both in var and arrays, for different reasons, actually. But you cannot really edit in place your store noun. And so what you would have to do on each invoke, on each call to invoke function, you would have to copy the entire store noun, you would have to mutate it, and eventually you would discard the old copy. But there is this constant reallocation copying happening at each invoke call. And remember that in our previous example in foo function, you need to do this 5 times in order to just, I don't know, parse a string or something. And this is just like one of the problems, which is the major problem. Another problem is that if you want to jet your WebAssembly interpreter with some other WebAssembly interpreter implementation in C, well, then you would need to marshal that store noun into some kind of C struct, which would be recognizable by this WebAssembly interpreter in C. And then you would need to mutate it by calling a function, a Wasm function, and then you need to marshal it back into a noun. So there is this constant serialization, deserialization overhead. You can kind of sidestep this if you design your store noun to be as close as possible to the way it is represented in a Wasm interpreter in C. But that really couples the Hun code to the jet. And it kind of goes against Urbit ethos, where the Hun code is sort of a specification of an algorithm, and the jet is an implementation of the algorithm, but now the two are coupled. And so you need some other approach. And the way I went with it is that I developed a Lea language, which is higher level DSL, and it comes with an interpreting function which takes a module. Module is just, well, octs is a pair of 2 atoms. The first atom is a length of a byte array, and the second atom is the byte array itself. So it's basically a length prefixed byte array. It takes this module and takes code where script is it's a higher level script which actually encapsulates this entire function called graph. It takes the script, it takes the input parameters, which is list of values, and a value is either a WebAssembly value, so again, fixed size, 32-bit, 64-bit integer or float, or it's, again, a byte array. And so the language itself has kind of a subset of WebAssembly arithmetics, but a superset of types, and has some additional operations in order to perform operations on strings. Just one small caveat is that code here is not just a pair of a script and a list of values, but it's actually a list of those things. This is how you would get stateful interactions with WebAssembly across events. Because you cannot, for example, I don't know, send a packet during jet execution. And so you would do something like, okay, call a function, then you would react to the effect, to the output by sending some kind of effect, like maybe perform a remote scry or something. And then if you want to invoke some other function statefully, kind of remembering what happened before, you would just append a new pair of script and list of values to the end of the list. And then you would just rerun the function again. And this is an example of Lea script. This example, so this is in text format of Lea, which is not actually yet implemented. So this is kind of a desired way in which I want Lea language to look like. So this is, again, the example with calling a foo function from string to a string. You declare that it takes a single parameter, a, which is a byte array. And then you call different functions in order to allocate memory on the stack, on the heap. You write the string into at the pointer in the memory, and then eventually you call foo function, and then you extract the string. So this is this is the text format which would be parsed into Lea abstract syntax tree format. For now, the parser doesn't really exist, and so instead scripts look scripts look something like this. So you basically write this big noun in AST format. It's a little bit messy because this linearization algorithm that I use is quite dumb. So you have to reiterate the type of the variable on each use side. But it's OK. It's something that I can handle later. And so this brings me to actually how I execute Lea. As I was developing the language and the interpreter for it, I saw that it was a very thin overlay or WebAssembly. So instead of trying to make a runtime in Hoon and then to make another runtime in C, I decided to compile Lea to WebAssembly. And so you go first through a linearization step, where you take the script that you saw before, and you replace lexically scoped variables with accesses to an array of Lea values. And then you compile it to WebAssembly, where in WebAssembly it is implemented as an adjacent memory array of values of arbitrary size. And so each WebAssembly module that is compiled from Lea, it comes with a garbage collector and an allocator and a bunch of API functions in order to store and load Lea values. And then once you compile Lea to WebAssembly, now you have two WebAssembly modules, the original one that you intended to run and the one that came from Lea that actually scripts the first one. And then you just link them together and run a main function from Lea module. It's quite simple. The question of interactivity is, OK, so Lea, as you saw before, it does not return the state of the Wasm virtual machine. It only returns the Lea results. And how do you set up interactions? So for example, with the previous layout where we had the invoke function, it was trivial. Like you had the store noun, which was representing the WebAssembly virtual machine state. And then you can just store the state, let's say in a goal agent. And then each time you want to call a function, you provide the state, you obtain the new state, you update the state. That's it. And asynchronous FFI, so here I mean is that in WebAssembly, you can, in theory, import functions that require you to send effects in order to resolve them. So think, for example, remote scries. Again, it's somewhat trivial in case with invoke gate, where you just basically this store, it allows you to store your state of suspended WebAssembly virtual machine, then you can just kind of continue the execution. But you cannot do this with Lea directly. So how do we do this? Well, with interactive calls, as I said before, you just append a new pair of script and input values to the end of the list, and you just rerun the whole thing entirely. And similarly, with asynchronous FFI, in input parameters, you also provide a shop, which is a list of resolved external function calls. And then each time Lea interpreter encounters an external function call, it inspects the list. And if it sees that it's empty, it then blocks. And it returns you kind of a request for external function call. And then your embedding environment, which, for example, could be a generator or a thread or a goal agent or shrub, then performs this external function call. And then it injects the result into this list. As for an example, I can actually show it right now. Oops. OK, so this is some Rust code. And it's quite simple. All it does is that it imports a function wish that takes a vector of characters and returns a vector of characters. And what it basically is, well, a wish is just a Hoon interpreter. It takes a string, which is Hoon code, it evaluates it, and returns a pre-printed result. And so we have our function run, and what it does is that it calls this wish interpreter on this string, which, well, it calculates a mag hash of 42, and then pre-prints it to kind of get rid of dots. And then you can, let's say, extract the result. You can parse it directly in Rust, and you can add one and return it just for fun. And, oh, it doesn't fit. 1 second. I can actually run it. And returns the result. It was a little bit slow because the interpreter here is not jetted, because the FFI interactions are not, the FFI interface is not provided in the jet right now. So you can kind of imagine how slow it would be in some other cases. Which, well, that brings me to the topic of jetting. Actually, jetting Lia is not that hard because the entire logic of Lia interpreter is compile Lia script to WebAssembly, link two modules together, and run a main function. And you can just have the same logic in C pretty much. You don't need to jet Lia to WebAssembly interpreter because that's not where the bottleneck of performance is. And you don't need to jet the Wasm interpreter itself. You can just take another Wasm interpreter written in C. In my case, I'm using a Wasm 3 interpreter. And for example, this is how I used the WebAssembly interpreter in my case. So WebAssembly comes with two formats, with text format and binary format. And at some point in my project, I needed to convert from text format to binary format. And I was a little bit lazy. I didn't want to write the converting function myself. And so what I did is that I found a Rust library that does that for me. I compile it to WebAssembly. And I run it with my WebAssembly interpreter. Thank you. In fact, I did this back in January. It's just that it was stupidly slow. But now, right now, I'll boot there with the jet. And the function that I'm going to run, I'm going to parse the same module as from the example in the slides. I'm going to parse it twice. I'm going to parse it with the jet on and with the jet off, and I'm just going to compare the results with .tis. And, well, hopefully, they're going to be the same. So it's going to be with Lia. So the jetted version is already done at around 100 milliseconds. Most of the time is actually, it's like 2/3 of the time is spent on running knock within Lia, which is compiling Lia to WebAssembly and then encoding this into binary format to provide to the Wasm interpreter in C. And so right now the unjetted version is running, and it took 5 seconds to actually parse the binary format, and it's going to take some time. So for now, yeah, this is the breakdown of the time it takes in the jet. As I said, 2/3 of the time is spent on running knock. It could be amortized, like you could reformulate the jet a little bit so that it would take just the WebAssembly modules, the original one and the one that came from the compiler, so that you just compile ahead of time and store it as a noun. You need to perform some kind of health check to check if the second module is actually a module that came from the Lia compiler to make sure that, yeah, okay, it has all the necessary imports and exports and so on. But then you can remove like 2/3 of this time. And then the actual WebAssembly execution is something like, in this case, it was about 32 milliseconds, and I compared to the same runtime in browser, and in browser it's about 2 times faster, 2 to 3 times faster, which it's not terrible, like it's okay. Could probably live with this. Let me actually check if the unjetted version is done. Yeah, it's done at 60 seconds, and the results are the same. Perfect. Another way in which you could use Lia interpreter is to quote-unquote jet algorithms that would be slow in knock, which usually either involves some kind of string manipulation or like byte array manipulation, or it's highly recursive algorithms. Highly recursive algorithms, this is because, well, in VAR especially, because you have overhead of gate calls, and with array manipulation, if you have a byte array, and if you want to like change a single character in the byte array, if this byte array is an atom, you need to actually reallocate the entire atom. Or alternatively, if you're working with tapes, you would need to reallocate parts of the tape. And as examples, I calculated an Ackermann function, which is a highly recursive function, without caching. And without caching, Wasm interpreter, when jetted, outperforms by a factor of 3 the native Hun implementation. Actually, I tried to do this with caching. So in Hun, you can jet it with, you can cache it with siglas. And in WebAssembly, I made a hash map of the results. In that case, Hun actually outperformed WebAssembly implementation. So I guess we have some kind of overhead of modeling hash maps in WebAssembly. And another one is a BrainF interpreter. BrainF implements a virtual machine, which is like a very simple Turing machine. It has a pointer that goes along a tape and changes characters in it. And the best you can do in Hun is to model this as a pair of tapes where you kind of pop the character from one of the tapes and push it onto another. But it's like cell allocation for each move of the pointer. And WebAssembly, this is just pointer increment, decrement. It is very cheap. And so you get like 6.5 factor speed up if you do this in WebAssembly. And this is with the entire overhead of compiling here to WebAssembly and so on and so forth. And finally, I'll describe what is actually left. So first of all, in the jet, I need to add foreign function interface support. It's not that hard, just need to sit down and do this. Another thing is that right now, jet is not allocating on the loom. Which is just the original interpreter, Wasm 3 interpreter uses malloc from C. It just needs to be patched. Again, it shouldn't be that hard. The final point, well, not the final point, but another point is the determinism of virtual machine. So in order for jet to actually match, so in the example that I gave before, the jet matched. But this is because there is no floating point arithmetics. With floating point arithmetics, it is likely that there will be an unmatch because Wasm specification, it does not specify exact results for floating point arithmetics. It allows you a set of results, and you can return any value from the set. And if you return any value from the set, then your Wasm implementation is correct. And so I just need to make sure that whatever is returned in Wasm 3 is actually the same what is returned in my Wasm interpreter in Hun. And finally, I need to finish the text format for Lia. This is just kind of quality of life for development. So these are like simpler issues that need to be solved. A harder one is caching of the store, which in Hun it would be a noun. However, in the jet, the store is represented by some kind of C struct in the jet. And if you don't cache it, then since on every interaction you append either a new instruction or a new result of an external function call, you append it to the end of the list, and then you rerun your interpreter completely. That means that for entire lifecycle of your interactive script, the time complexity is O of n squared, which is just, it's not good. And the instantiation is O of n. And instead, it should be O of 1 for instantiation and O of n for script evaluation. And the way you could fix this is by having something like persistent memorization in the jet. It's not actually persistent memorization, because persistent memorization saves subject and the formula kind of as a key, and the product is the result. But here, as a key, you would need to use something like arguments for the jet, and the result is like virtual machine, Wasm virtual machine struct in C. And then you need to actually persist it across events. And if you can do this, then, well, stateful executions across events become a lot better. And so, yeah, this is it. If you have any questions, I'd be glad to answer them. Just before moving on, I wanted to say thank you. I don't see Edward here. I guess he's busy right now. Just want, well, I just want to say thank you to him. He really helped me with figuring out a lot of things in WebAssembly, and especially with code gen, so like linearization algorithm. And Joe, Master Mozart, he's not here too. Oh well. I just want to say thank you to him too. He really helped me figure out the API of Wasm 3. Yeah, that's it. Any questions, please?
What sort of are the big functions, or like the big use cases that are blocked by not being able to have stateful function calls?
Something like goal agents, essentially. I'm not, and I guess like shrubs too. But initially, as I was developing it, I was thinking about goal agents. So here's the thing. Without store caching, you actually could have a goal agent. However, if you wanted this to be somewhat performant, you would need to return the state of your goal agent in Rust on every call. And then you are like back at the same problem here. Like if your state is small, then I guess you're fine. But if your state is big and like serialization, deserialization is not trivial, then you really want to have caching of this Wasm state. But for running like things, let's say, statelessly, like for example, calling a parser function or something, it's not blocked. You could do this without caching.
Just one other use case for that we talked about a little last night, but there's a full Wasm implementation of SQLite. When you have stateful preservation across calls, you could actually have an embedded SQLite database that you load your data into and query from within Urbit, and you've got SQL in Urbit, and that's kind of cool.
Another example would be, let's say, interactive Python shell. If you don't have caching, then every next script would take as much time as all the previous scripts combined. And so, yeah.
Do you have a copy of the breakpoint that you're going to do?
Of course.
Can you send it to me?
Sure.
Awesome.
I have two, actually.
You have two? Oh, cool. Okay.
Well, one is with tapes, as I described, and another one operates on the atoms. It's 2 times slower.
Wait, really?
Yeah. You, please? No, you're on front.
So, in the case where I have some Wasm that I've acquired that I want to run into, is it my responsibility to figure out the API and write the Leah script to?
Yes, essentially yes. However, it is somewhat, it is made simpler usually by the compilers. I usually work with Rust, and Rust compiler would produce the JavaScript. And then all you need to do is just translate it from JavaScript to Leah, which is quite straightforward. It doesn't really take a lot of brain power.
Well, if you're compiling it yourself, you can generate the Leah.
Sorry?
If you're generating the Wasm yourself, you can also generate the Leah at the same time, basically.
Ideally, yes. I would like compilers to also generate Leah in addition to JavaScript. But maybe it's too much to ask from compiler developers.
Is there a cost to keeping around this state, like compute-wise?
Well, if you talk about the caching, which is not yet implemented, but yeah, of course, there is a cost because it would basically be, let's say in their terms, it would be on surface road. This is where you would need to save it. So from time to time, you would need to kind of lose this cache. This is why, as one of the input parameters in Leah, there's kind of a hint argument, which is ignored in the home code. But you could, and it's just an atom, a term. But Jet could inspect this atom and say, okay, like this hint tells me to use such and such caching strategy, which maybe don't cache it, or maybe prevent actually save this cache for future events, or maybe like save this cache only within like this event or something like that.
Does this block the event loop, by the way?
I don't think so. No.
Okay, gotcha. Yeah. I guess like, what if you wanted to run, let's say, like a client for, like a node for like blockchain, right? Theoretically, like, would that block? You know.
Well, yeah, I see. So when you call a function, when you call Leah interpreter, and the WebAssembly module that you provided, it imports some kind of function that needs to send a certain effect. Let's say, send a packet if it's some kind of crypto node. You want to send a message at some point. Then it would get blocked, as in it would return you a result. So let me just show this. So one of the here the nomenclature is the same as like in Mink interpreter. So like 0 means okay, success. 1 means you got blocked on an external call request. And the request Leah is like the name of the function that WebAssembly interpreter wants you to run and the provided arguments for it. So you then go ahead and run it. Let's say it's a spider thread or it's a shrub, whatever, something that interacts with the outer world. You get the result. You put this into the list of resolved external function calls, and then you call the interpreting function again, but because the state was cached, you wouldn't just rerun it from scratch. You would just start off from where you stopped, if you have caching. Right now, there is no caching.
This is silly, but is it possible to use the web browser's implementation of the Wasm interpreter somehow?
I'm not really actually familiar with the way.
Me neither. This was a
Right.
Well, in theory, yes, and I don't know how much of a pain it is.
Yeah, that's what I'm
It's open source.
Yeah, yeah, that's what
Yeah, like if Chromium is open source, and if Chromium is written in C, then I guess you kind of
It'd be cool.
would try to extract it.
It's written in C++, I think.
Oh, gross, then.
Yeah.
Never mind.
Yeah, yeah.
We don't want to do that, it's fine.
No wonder. It might also be huge.
Yeah, that might be really fun.
Like there are also a lot of optimization techniques. Like when I tried to run the parsing function in the browser, the first time I got the result of 16 milliseconds, I run it again with the same arguments. It was done in 100 microseconds. Like there is like a lot of caching, a lot of like memorization, and like, do you really want to have all this?
But yeah, I also was wondering, like, if, I don't know if they're jitting WebAssembly or what, but I was wondering if they're just, caching, parsing, and compilation in a way that we could also do, right? Like, could we kind of break it up?
It's the boat.
Yeah, I guess, but like, I was wondering, like, it is the boat, yeah, it's a money pit, but like, would it, I don't know if you have some idea of like whether those are sort of relatively simple things to cache, if you could break up sort of compiling, parsing, running.
Well, yeah, right.
Caching, parsing separately.
Right, you could reformat the jet a little bit where the jet only takes the WebAssembly modules, so the original one and the one compiled. And then ahead of time, you could perform the NOC computation, just store those modules as a noun. Yeah, that's reasonable. And then you would only spend like whatever, 30 milliseconds, so like twice the time of the browser to compute WebAssembly. Then yeah, it's fine.
Yeah.
But it doesn't really make sense if, for example, you have some kind of interactive session, because you cannot, it doesn't, yeah, sure, you could compile it ahead of time, but you are only going to use it once, so it doesn't really make sense in this case.
Yeah.
And also, just one more thing, in the jet, which would take only 2 WebAssembly modules, you cannot really have the same store caching thing, because now you don't really have the arguments which you use as a key. As far as I understand. I need to think a little bit more about it.
Yeah. Well, I mean, in terms of the performance of the Wasm interpreter, Wasm 3 is a production Wasm interpreter, right? Isn't that the one that like most of the blockchain projects use? Like Cosm
I
Wasm?
have no idea.
I think it is. I think it's like,
It is
isn't that like
what it is, yeah.
Wasm for Web 3
I
or
think
something?
so.
That's why I call it.
Yeah.
Yeah.
So,
So it's not like it's a dinky.
No, 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 no.
It's like a real thing.
Any more questions? Yes, Jack?
So I'm obviously not an expert in these things, but I know I'm going to be all working on matrix multiplication and machine learning stuff. And you mentioned that Leo might help with jetting various things that are otherwise slow. So I'm just wondering if you might be possible.
Yeah, I can see how it could be faster in some kind of like array mathematics, where it's just like faster to work with an array in WebAssembly than in like linked list or something like that in NOC. There is, well, but you probably want to parallelize this ideally. And natively there is parallelization in WebAssembly in terms of SIMD instructions. The particular version of WebAssembly interpreter I'm using, Wasm 3, I don't think this version actually supports SIMD. Maybe newer versions do. I need to double check. But then again, it is somewhat trivial to like replace a Wasm interpreter if I find another one that supports SIMD. SIMD is single instruction, multiple data. So like per one instruction, you can do computations on a bunch of numbers. So that could speed things up. In fact, there is a neural network implementation in WebAssembly, Stockfish, which you can run in browser to like compute chess moves. That uses SIMD, and it's like way faster because of SIMD. I think there is also Whisper implementation in Wasm. I think it also uses SIMD. Without SIMD, it would be way too slow.
Well, would it make sense to use the same general strategy of Lea or something like Lea as a way of running other languages that aren't Wasm
And I was wondering, like in Urbit, but taking a similar strategy where you write something like Leah, but for not for invoking assembly, but for invoking some other language. And in particular, I was wondering if there maybe, for array languages, I was wondering if that might be particularly useful, where maybe you don't have to like, deal with sort of making all the intermediate products, the intermediate arrays, like actually nouns, where you have to like stick them on the loom and prepend them, put the one in front of them, and make them real nouns. Like, is there? Would that
Yeah,
make
I can
sense?
see how it could work, and if it was like some kind of higher level language, Racker Hattas is working on Lua, I believe,
Yeah.
and as far as I saw, like, I remember in the grant proposal, he wanted to do a similar jetting strategy with like Leah style jet, and yeah, I think it could be done. It would be easier because now you don't have to like translate JavaScript to Leah or something. No, you just take Lua code and you just run it in a similar fashion. I could see how it could work. Yeah.
So I was thinking, would it be possible to somehow use this to jet the actual thing code? Because currently, imagine you're in user space, and you have some application which does like array processing. It's impossible to do efficiently in Pune, so you have to have jet squares. So could we have that and somehow hook it?
Well, yeah, right. This is what I kind of mentioned is that, well, jet quote unquote, because like actual jetting, which would mean changing the knock interpreter, but you can run certain algorithms faster in jet at WebAssembly than you would in native H. And so, yeah, one of the examples is brainf interpreter. It actually it runs faster in Wasm than in native H, or whatever Ackermann function.
Yeah, but is it like I have a G code and so currently if I want to do that, just put a hint, right? And I have a jet in runtime. So I was thinking about putting a hint, which then instead of me going out and writing SQL for that, I could somehow do this, some mechanism for that, so that.
But then you would need to like translate Hun or knock even to Wasm, and I think there's just too much overhead. I don't really see how you can do this.
Instead of a hint, you just import the Wasm module and you call it as though it were just a Hoon function. You're calling it that in place of a Hoon implementation, but it works the same. So you just use a.
There's a little bit of overhead there. It's not the same, right?
It's not the
You
same
could
as a
have- you
jet,
could
but
also-
it serves the same role.
You could also have a metacircular knock interpreter that can take in Wasm jets, right? Then you can write in Wasm, and then basically, if you say like the add function was jetted with this Wasm module, right? Then that metacircular knock interpreter would run, but whenever it hits a knock function that's jetted by one of those Wasm modules, it would run the Wasm module instead. So you could do that. And then you could also have the runtime use, so that's one thing that you could have on its own, which might be useful. That might be what you're asking about.
I mean,
It's similar.
because currently, like, is there even a roadmap for like, having user space just? There is not, right? It's not even technically. I mean, it's a trick that you can run just in user space, but there's no.
There are a bunch of different plans for how you could sort of define jets in user space and have the runtime take advantage of them. But what's cool about WebAssembly is that because you can run it deterministically, like it could be sort of a virtualized jetting system if you wanted it to be. It won't be quite as fast as native code, but you could do that. And so,
Yeah, I think the biggest gain you get is that you just don't have to go and write the thing yourself. You can do what he did.
Yeah, like, you don't have to run the.
Someone else wrote this algorithm. I'm just going to pull it in, compile it, and call it there.
Right. If you have Wasm in the first place, like why writing Hun? Just import the Wasm module and run it. You wouldn't have to like run the write the implementation twice.
Sometimes you have Hoon code and it actually works pretty well. I mean, even for yourself, right? And it is just maybe single function that you want to jet. So it's really not cool that you have to go out and write SQL all the time for this kind of use case.
I mean, there is a NOC 13 proposal, but I'm not sure about that.
there's also another layer where Wasm could be useful, where it could be that you could ask the runtime to install a new jet, even if it's untrusted, and so then it would compile the jet to Wasm and then run it, right? And then at least that code is that's at least safer than doing like a DL open, where you like load a dynamic library some options in there too, I think.
Would you be able to like restrict for some kind of like, I guess like more sandboxed like running of code? So you might want to, so you can have some semblance of like verifiable, let's say Rust or Wasm, like
Well, you can have.
like risk architecture kind of.
I'm not sure about sandboxing the Wasm code itself, but when the Wasm code calls to external functions, you can just inspect those calls. Those calls are just nowns, and you could filter them. You could check, okay, does it call this function, or does it call some other functions that I didn't want? And then in the embedding environment, so in whatever, in the Go agent or in Shrub, you can just choose like which, let's say, spider threads to link. And you can just choose not to link a certain thread. Or you can choose to inspect a noun to make sure, like, okay, if you want to do something, you can read from this part of the immutable namespace, but not from this part. And this could also work. Or like you can emit such pokes, but not the other kind of pokes. You could just check it like in the Hoon environment itself.